thank you everyone for attending this morning. So today we're going to talk about device firmware update best practices. Firmware update is so essential to our work as firmware engineers. I think most people on this call will have implemented it at least once. It's something I've had to do many times in my career. And unfortunately, there really isn't too much content out there or too much information out there on how to do it right. So today, what I hope to do is share some of the things I've learned during my career and discuss some of those best practices with you. Of course, the topic is so vast. Firmware update is such an interesting and complex topic that we won't hope to cover everything today. So we will likely have follow-ups in the future, and I look forward to receiving feedback from you at the end on what else you'd like to learn about. But first, a little bit about me. My name is François Baldassari. I'm currently the founder and CEO at Memfault. Memfault builds infrastructure and tools for firmware engineers. As you can imagine, tooling and automation in software engineering is my passion. I've been building internal systems and helping teams be more productive throughout my career at companies like Pebble, Oculus, Sun Microsystems, and now Memfault. I've seen a few of my ex-colleagues in the attendee list, so hello everyone. These days, I write on Memfault's Interrupt blog, which you can find at interrupts.memfault.com. There's also a fantastic Slack community, which you can join from the Interrupt website, where I spend a lot of time discussing these topics with some of our colleagues. Today's agenda covers two main topics. The first one is firmware update architecture, or in other words, how might we design the update process on device to make sure it is efficient and safe. And number two is firmware updates distribution. How do we get firmware from our devices, from the cloud to our devices in a way that is cost effective, works every time, and allows us to quickly pull updates if anything goes wrong. But first, I'd love to ask you a question. I think there's, at this point, about 70 or so firmware engineers on this call. So I'll be very curious to hear whether any of you have shipped a product without firmware updates in it before. So we'll wait a couple, minutes or a minute for everyone to vote, and we will share the results. Okay, so it looks like we're about evenly divided. Half of us have shipped devices without firmware updates, and half of us have not. I'm in the second camp. Every product I've ever shipped has had firmware update capability. You might say that this is because I don't quite trust my work. I really like having the kind of last resort of updating my firmware if anything goes wrong. But of course, we don't always have that luxury. Some devices don't really have even a path for updating firmware. Others, might be on a very tight schedule or might have security requirements that preclude firmware updates. But I want to talk a little bit about why would we need firmware updates? What are the reasons to add firmware updates so that perhaps in your future projects, you can convince management that this is really important. And so I'll go over a couple arguments that I find convincing. The first one, and as much as we hate to hear it, you are bound to ship bugs in your firmware. Jack Gensel says that per every 1,000 lines of code that we write, there's between 10 and 100 defects. These numbers are I think, crazy. I find them a little bit intimidating, but I trust Jack Gensel to have done his research. And so you can see that even the top 1% of engineers on average produce 11.2 bugs per 1,000 lines of code. And this is because, we can't anticipate all users' inputs. I think one of the things that I've learned in my career is that no matter how hard I try, I'm always surprised by the crazy ways in which end users use my devices. But also, I think our devices are increasing in complexity, and QA just simply cannot catch every issue. And so if we are destined to ship our devices with bugs, there's really only one way to protect ourselves against the consequences of that, or at least most consequences, and it is to be able to update our way out of a particularly bad bug. And in fact, even the best among us do this. This is a quote from NASA's Curiosity mission. So that's one of the Mars rover. And they were talking about the third upgrade of the firmware since the landing of the rover, and that in fact, when they upgraded from version 11 to version 10, they ended up having a crash bug and had to roll back the updates. Since then, they fixed the issue. But you can imagine NASA with their extremely rigorous processes, their very intense QA and well-documented testing regimens. If even they have to rely on firmware updates to fix bugs in production, I think most projects do. And in fact, we all fall prey to the law of large numbers. There are bugs that I call the 10,000 hour bugs. They happen once every 10,000 hours. That means that in QA, they are impossible to find. And so these bugs, they'll be found in production, because once you have 10,000 devices out there, you'll be looking at, they'll be happening all of the time, let alone at 1 million devices. So whatever you do and whichever project you're working on, every night you're testing in prod. You might think, my code is really good, I don't have to worry about this. And unfortunately, even if you were the greatest firmware engineer out there, you're not immune to other people's code leading to problems in your device. And in fact, increasingly what I see is third-party software being leveraged in firmware projects. This includes chip SDKs most commonly, right? So you might be using the BSP from your chip vendor. You might even be using an RTOS that they provided alongside the SDK. But also protocol implementations. Very few of us implement our own Wi-Fi stacks, Bluetooth stacks, and other complex protocol stacks. There's also third-party libraries. The most common one I see is cryptography library, right? Things like Wolf SSL. And so you'll find bugs in these, of course. And unfortunately, this third-party code is so important to the functioning of your device that bugs that are found in that code will be very serious. And so you'll very likely want to update your device when you find those. And even if they're not bugs, sometimes just maintaining compatibility across protocols will require updates. Bluetooth, Wi-Fi, USB, they're living protocols. And to stay compatible with the latest devices, you might need to update the implementation of that protocol, or even do things as simple as update SSL certificates that are built into your firmware, because SSL certificates have an expiry. And so if your device is going to live for 20 years, you eventually won't be able to talk to anything in the cloud because all those SSL certs that you're meant to recognize will have expired. So firmware update capability future-proofs your device to some extent. Here's a concrete example. The Bluetooth low energy implementation in the PSOC, that Cypress kind of Bluetooth microcontrollers, their BLE 4.2 components, earlier versions of it, basically had a broken random number generator. Random number generators are crucial to cryptography. And in this case, what that meant is that an attacker could, in effect, decrypt the BLE traffic between the Cypress device and whatever it was talking to. This is a serious bug. It was assigned a CVE number. And if your device was impacted, you sure would have hoped that firmware update was implemented. Otherwise, your device is compromised. Imagine this is a Bluetooth audio device. Now people can listen in on what that device is transmitting or receiving. So being able to update ourselves out of a security flaw or a very bad bug, extremely important. Last but not least, and this is perhaps the most hopeful, I think up until now I've talked about all the things that could go wrong, but let's talk a little bit about things that could go well. Firmware updates actually enables us to ship better products faster. Increasingly, I see teams, embracing more agile development workflows. And the way this looks is we ship an MVP and we iterate. In the hardware space, one of the most common manifestation of that is what I often hear called a day zero update. So a day zero update is when you freeze your firmware in an incomplete state when you start mass production and plan to do an update at launch when the device is in customers' hands to complete the functionality of the device. And so the advantage of a day zero update is huge. You can see in the diagram on the right. If we have a traditional firmware development model where we freeze the firmware when we start mass production, we end up, it means that our firmware has to be ready months before launch. Oftentimes the ramp before, when we start mass production, ramp takes about 3 months or more even to build enough inventory to launch the device. And so if we freeze the firmware before that, we lose out on 3 months of development between the beginning of mass production and launch. If we do a day zero update and if we enable software updates in our device, we can actually develop firmware up until the very end and the very launch dates, which means that we can actually pool our launch dates and start mass production in effect 3 months earlier. And so on top of having the ability of continuously improving our algorithm, continuously improving our products, we can even ship it faster. This is a huge benefit. So now that we've talked about why we need firmware updates, and hopefully I've convinced you that this is really important and something that every product should have, let's talk about how we might implement firmware updates. And it's really important to do this right. Why do we need to do this right? Well, there's a lot that can go wrong if we don't do firmware update properly. Firmware update is one of the more sensitive subsystems in your firmware. And this is why many of us are always a little jittery when we click the release button on a new update. Done poorly, there's a very real risk that will break our devices. You've all seen the image that I've put on the right on this slide. When a device tells you, please do not disconnect power while this update is in progress. To me, this warning is a little bit scary, right? Like, what will happen if I disconnect power? Is there really a way that poor user behavior can break my device? That's very, very scary. And I think that we must make sure that that is not the case. In my opinion, if your device will fail, if it loses power during an update, then your device has a serious flaw and should be re-architected. So I'll talk through 4 principles for safe OTA design on a device. Number 1, the firmware update code needs to be separate from the application so that churn in the application does not impact the firmware update code. Number 2, the firmware update code itself should be updatable so that if it itself has a bug, we can bail ourselves out of that. Number 3, failure mid-update should be recoverable. So none of that, don't unplug power during updates. That is not acceptable. And number 4, you should version your non-volatile data. I think too often people get caught unprepared trying to change the serialization of data on disk or on flash and realize that they don't have a good mechanism to do that. So I'll go over these in details. First, firmware update code should be separate from the application. I learned that lesson the hard way. I remember we shipped an update. I think it might have been version 3.6, but perhaps the Pebblers in attendance can correct me. At Pebble, and when we shipped that update, we realized that the devices on that version could no longer update to new versions. Unfortunately, we didn't find that until we pushed the update to production. And so we end up with a large number of watches out in the world that could no longer update from the version they were on. And we were really puzzled. So of course, we immediately stopped the rollout of that update. But we were really puzzled because we had not changed the firmware update code. The only code we had changed was unrelated application codes around, connectivity and around some of the UI. And so we started digging. And what we found is that there was an uninitialized variable in our firmware update code that up until now had been set to 0 by happenstance, because that area of the memory was set to 0. And in the process of changing other parts of the code, we shuffled around the memory location, we shuffled around what order things got executed in, and now that uninitialized variable was set to 1. Of course, we would have rather not have had an uninitialized variable in the first place, but had our application code not changed, our firmware update process would still have worked. This was not a good week at Pebble, and some of my colleagues spent days and nights trying to figure out a way to update ourselves out of this mess. And thankfully we did, but we may not be so lucky next time. And so since then, I've advocated that update code and application code be kept separate in separate programs, so that no matter what you do in your application, which necessarily needs to iterate a good bit and change over time, your firmware update code stays the same. And so the way I'll do that, and this is the first of several architectural diagrams that you'll see, is that I'll typically put the update code in my bootloader and the rest of the code in the application. So when the device starts, the bootloader will check whether there's an update for it or not. And if there is, it will update the application before it loads it. If there isn't, the bootloader just loads the application as it usually does. Number 2, firmware update code should be itself updatable, because if the Gensel rule of 10 bugs or 100 bugs per 1,000 lines of code applies to application, it certainly applies to firmware update code as well. So in all likelihood, there'll be bugs there, and you'll need a way to get out of that. So how do we do this? Here again, in order to keep up with the previous rule, which is that our update code and our app code need to be separate, we need to create a third program. So here I'm calling it the boot updater. And the boot updater's only job is to update our bootloader. So when we start our device, what we'll do is we'll see whether we want to update the bootloader. And if we do, we'll start the boot updater. It will update our bootloader and we will go back to our normal flow. Otherwise, we load our application and we continue as normal. So in teal here, you see the updates to our architecture diagram and what has changed from the previous one. By the way, if you have any questions about this, you can click on the Q&A button in Zoom and add your questions so that we can get to them towards the end. I know some of these diagrams are a little bit complicated, so don't hesitate to ask me to explain them in more details afterwards. Number 3, and this is a big one, failure mid-updates should be recoverable. So if we go back to our previous slides, we can see an obvious flaw with this, which is what happens if the update fails in the middle of updating our bootloader? Well, let's say I yank the power while my bootloader is mid-update. Now I no longer have a valid bootloader. So next time I power the device, I'm going to execute an invalid program and I'm basically hosed, right? My device is bricked at this point. So what can we do about this? Well, we need to add a little bit of complexity. We need a fallback in the event that our bootloader update fails. And so what I recommend here is to actually split your bootloader into two. A primary bootloader, which is immutable and whose only job is to load other programs. So it's what I would call a traditional bootloader. You can't update it, but it is extremely, extremely simple. And you have a secondary bootloader, which is the program we had up until now, which can update things, load them, and is a little bit more complicated. And in the events that we failed to update, that we basically disabled our secondary bootloader because we yanked the power mid updates, we can basically fall back to our first bootloader, which will see that there's an invalid program where the second bootloader should be, and we'll instead load our boot updater so that we can update ourselves out of this mess. So this architecture is a little bit more complicated. It has a few more moving pieces, but in practice, it is not so difficult to implement. And in fact, you will find a full implementation of this on the Interrupt blog and in the GitHub repository that comes with it. So in the end, we have a primary bootloader whose only job is to load the secondary bootloader or the updater. Number two, we have a secondary bootloader, which can load either the boot updater or the application. And then we have the boot updater, which can update the secondary bootloader, and the application, which just provides the normal behavior of our device. And with this, we have an architecture that, while it is a little bit more complex, is robust to a large number of failures, splits the firmware update code from the app, and is itself updatable. Last but not least, we need to make sure that we version our non-volatile data. So every firmware relies on some number of non-volatile data, whether it is a few structs that are serialized into Flash, or perhaps even just data that we keep in no init RAM that stays powered. And that non-volatile data will sometimes need to change from version to version. But if we don't think of this ahead of time in our firmware, as part of our firmware update process, and we don't have a good way to migrate that data, then changing those data structures becomes very difficult. And so I typically recommend that 3 fields be added to all of our non-volatile data structures. The first one is a version field. 8 bits is more than enough, and you can just make it a simple integer version. No need for semver or anything like that here. The second one is a commit bit. So typically on a flash, on a flash memory, you reset it to 1 and you set it to 0. So the commit bit is a bit that when it's set to 1 means the data is not yet committed, and if it's set to 0, it is committed, so that you know to verify that a data structure is committed before you read it. And then number 3 is an erase bit, so that you don't have to erase a full sector in your flash in order to just mark an old version of your data structure as invalid. So here again, when you set it to 0, it becomes erased, and your code should no longer read it. And with that, you can implement migration functions that go from each version to the next. So let's say that you've arrived at version 4 of your structs. You will have a migration function to go from 1 to 2, from 2 to 3, from 3 to 4, and then add more for future versions. That means that if a person has a very, very old firmware that they've been keeping on their device, which they haven't powered in a year, they can turn it on, they'll go through all of the migration functions and be updated to the latest. So that concludes the architecture part of this talk. The question that we answered so far was, how do we implement firmware updates on device in a way that is safe, is effective, and allows us to bail ourselves out of all kinds of poor situations. Next up, I'm going to talk about something that on firmware teams, I think we don't always worry about enough, which is how do we get our updates from the clouds or from wherever they're hosted to our devices effectively? And what are the couple of things that we need to make sure are there? What are the couple functionalities of the distribution system that are really important? And so first we'll do a second poll, if you will, and I'd love to know what systems do you guys use today to host your firmware updates. So I've added a few. I'm sure I'll be missing some. If you select other, perhaps we'd love you in the survey we'll send at the end to tell us what you're using. Okay, we have about 70% of you all who voted. It's a great way to test how many people are paying attention. Let's see if we can get to 80. Okay, all right, never mind. So it looks like what we see. It looks like what we see is that the number one thing that people do is other. So I'll be really curious to hear what that other is, and I look forward to reading things in more details from all of you. We also see that many have built a custom server, which is really common, and others use Amazon S3 as kind of just a simple hosting system. So we'll talk about what attributes we need in this kind of a system. So of course, the most important thing that our OTA solution does, or our OTA backend does, is get the right firmware to the right device. And you'd think that it's pretty trivial, right? But in fact, what happens is, as a product line grows and evolves and changes, we typically will end up with a number of hardware configurations who will each need a different firmware, because we don't want to have every possible configuration compiled into a single firmware binary. We oftentimes can't afford it from a code space perspective. So instead, a very simple solution I see oftentimes used is that we host different firmwares at different paths. This is, I think, the typical way to do things with S3, which lets you create buckets with different paths and different names. And so perhaps we might have our website, which is foo.com, and we could have created static routes that say, /firmwares /hardware the hardware version. So in this case, maybe the hardware version is the name of your product, or it says EVT, DVT, whatever, however you version your hardware itself. And then latest for the latest firmware.bin. And your device will basically know to look at that static path in order to download that firmware. This works, but as devices get more complicated and as there's more and more diversity, it's a little bit limited. It also doesn't allow you to dynamically select what devices might receive what firmware. And so a better solution, and something that we should look for in firmware updates hosting solutions, is the ability to create rules for which firmware to send to which device. And all we need for that is for the device to tell us its serial number. So the device sends its serial number, we look it up and we see, okay, that device is this hardware configuration, and it's also a beta device. So I can send it to the beta firmware, and then our server will push a firmware back to the device. So simple ways to create rules based on serial numbers. It's not too complicated, but it can really give you the ability to do some interesting stuff, like create beta releases and perhaps send a release to only a very limited set of users who might be experiencing a specific bug. At Memfault, we call those cohorts. We can take this one step further and do what we call stage rollouts, because the second best thing to catching a bug before launch is to limit the blast radius. And by that, I mean, make sure that you've updated few enough devices that if there's a terrible bug, worst case scenario, you've only got to replace a few, right? You've limited the number of people who are impacted. So to do that, you can use kind of the previous simple system we talked about with the static routes. You can split your fleet into a number of hard-coded cohorts. So you might have put 10% of your devices in one group, 10% in another group, 10% in a third group, and you might push updates to them one after the other, right? Manually choose the first 10%, the second 10%. But of course, a better option is to have your OTA backends do this automatically. You want to be able to say, I'd like to update 10% of my fleet with this new beta release, and have your backend go and select 10% of devices, randomly sample them, and start the update. So that you can create, beta deployment, production deployments, just with some percentages and some simple kind of high-level description of who you'd like to get them, and not worry about assigning individual serial numbers to each update groups. So stage rollouts, I think, increasingly is a very important tool in our tool belt when we try to push updates and make sure that we limit the blast radius and we just incrementally deploy things to people. The next feature that I found really important is what I call must pass through releases. This is something we don't always think about ahead of time, but sometimes a version contains pretty intense, pretty complex migrations. And so you might not want to carry that migration code in every release in the future. But instead, what you want is to force devices to go through a specific version before they can update further. So for example, going back to our user with their device in their closet that hasn't been used in a while, they pull the device out and it's running firmware version 1.2. But today, the latest is firmware version 3.8. And so this is a pretty big change. And in fact, what we might ask them to do is to go from 1.2 to 2.0, 2.0 to 3.0, and then 3.0 to 3.8. So your OTA server needs to be able to, force the devices to go through that. Because if you have a simple latest firmware routes that the devices pull from, they'll get the 3.8 updates, and they may not be able to do that migration properly. And so instead, your server will need to kind of cadence or sequence that set of updates and return them one after the other as the device comes back with its new release. This is not something we can do with statically hosted binaries alone. This requires more intelligence, and this is why increasingly you can see many of you are building custom solutions. Last but not least, we got to make sure the firmware updates get distributed globally. Increasingly, this requires global infrastructure to do quickly and efficiently. And one of the things that really surprised me as I started building systems like that is that bandwidth costs are not trivial, right? Like if you look at AWS S3, for example, you might pay 5 to 10 cents per gigabyte of bandwidth. The storage is usually not the problem, but if you've got big updates, right? You're updating an embedded Linux device, then you might have a gigabyte update. And so if you have 1 million devices and you're trying to push a gigabyte to them, those 5 to 10 cents per gigabyte are going to add up to tens of thousands of dollars. That's the first thing that we need to contend with as we build kind of a global firmware distribution network. On top of that, we of course have to have servers in every continent to make sure that folks, wherever they are, gets their update quickly. The other problem you'll run into is the fact that your devices might all request updates at the same time, which creates very uneven loads on your servers. And so as a firmware engineer, it's really important that you think about this problem and that you add noise and you spread out the request for firmware updates to avoid what's called the thundering herd problem. And you can see on the right, I have an illustration of that problem. Here, what we see is basically a fleet of devices that are all on the same time base. So they're using an RTC and they keep precise track of time. And they check for new firmware on the hour mark every day or every hour. It's a very common kind of anti-pattern that I see. And so you see these huge spikes every hour because all of these requests come in. and those huge spikes, they're not good for your backends. This is what's called the thundering herd problem. They get trampled by all of these requests and your backend goes boom. So as a firmware engineer here, what you can do is add a little bit of randomness to the time you check the firmware update at, or modulate it by the serial number of the device, or some other parameters, the MAC address. Just find a way to just add a little bit of noise, whether random or not. And of course, no firmware update no firmware updates infrastructure is complete if you can't abort an update. Inevitably, you're going to have to pause or cancel a rollout in progress. That's just part of life. And hopefully, this is as simple to do as possible, right? What you want is a single button to click, or even better, a system that keeps track of error rates and automatically pauses an update if they reach a certain threshold. I've used at every one of my jobs, I've had to use the abort button. And in some cases, it's required multiple commands on the command lines, perhaps even logging into an FTP server to manually remove files. You don't want an error-prone process when you're in an emergency situation. You just need a single button to push. So whatever you build in your backend, as you talk to your engineering teams, or you talk to the providers that you're working with, you need to ask them for that. It's really important. And if you build your own, I've seen a pitfall that folks run into pretty regularly, which is that you might be caching your updates in your infrastructure. And so perhaps you've stopped serving it from the origin, but your caches might still be serving your updates. And it might take some time for that to propagate. So make sure that whatever you do, your edge nodes and your caches get flushed, so that you don't end up continuing to distribute the bad updates even after you pushed the abort button. And so, of course, these things I've learned because we've been building these systems at Memfault. We've, alongside our error monitoring system, which allows you to check for error rates and collects backtraces and crash information, as well as other types of errors from our devices, we've built a solid OTA solution, an OTA server that you can use to update your devices. It comes with global content delivery at bulk bandwidth prices. So you don't have to worry about the S3 costs when you push to 1 million devices. It lets you create those cohorts and those stage rollouts. It has the concept of a must pass through release, as we discussed earlier. It lets you even schedule releases so that your devices get updated at night rather than during the day. And most importantly, it has a single button you can push to stop an update in progress. So what I'll do before we open up for questions is I'll show you what that looks like, and then we'll transition to questions. Okay. So we're currently looking at the Memfault UI, and I'll start at our overview screen where you can see what's happening in your fleet. I won't talk about everything because many of the features here are not relevant to OTA, but you will see that from the get-go, you can look at the fragmentation of your firmware in your fleet. How many devices are running our latest firmware? How many are running an older version? And which versions make up our fleet. So here you can see that 30% of our devices run our 0.9.0 updates, and only 12% are running our latest. 36% are running our latest between two different hardware revisions. And so I'm going to walk you through creating a new updates and seeing what that looks like. So I'll click on the All Releases button here on the left, where we can see all the releases we've created to date. And you can see we've got a number from some development release with a Git SHA attached to some of our kind of major releases. So I'll click on the Add New Release button, and I'll give it a version number. Let's say this is release 4.0.0. If I use a version control system, which I strongly recommend you do, you can add the hash of that version in here. We'll create some notes like fix all of the bugs. And we can decide whether this firmware version is a must pass through release, as in if it needs to be updated to before we can go on to future versions. This one is not, so I won't check this checkbox. But we talked about that concept. It's a very important one. So here we go. Here I've got a release. We see that it was created a few seconds ago. It's not a must pass through release, and it's never been deployed. You'll see deployment history populate as we deploy it to new groups of devices. And of course, I need to upload some payloads. So I will skip this step for now, but what I can do is update some bin, add some bin files, add some ELF files, and even say which hardware revisions. So perhaps an EVT device will need a different payload from a DVT device. So we'll let you specify that in this box. When we have our firmware updates created, we can then go and push them down to cohorts of devices. So I've gone ahead and created 3 cohorts already. We have our internal cohorts, which is for our employees or internal users. That internal cohort is where we'll test the very unstable firmware. There are guinea pigs, there are employees. We have a beta cohort, which is users which are friends of ours and might tolerate a slightly kind of less stable firmware, but not quite as pliable as the internal users. And then we've got the production cohort, which is our other users, which we want to make sure only get stable firmware. And what I can do is I can go and update my internal users to my new release. So here we'll update to 1.0. We'll just update the entire cohorts. And what Memfault will do is just start serving that release to those devices. After a while, when we see that no new bugs have been reported using Memfault's issue tracker, we can go and push it to beta. Same thing, and same results. Memfault will start updating those devices. Last but not least, when it comes to go to production, we might want to do one of those stage rollouts I was talking about, where we start with a small percentage of the fleet and increase over time. And so what I'll do is I'll continue along the same path, but instead of selecting a normal update, which updates all the devices in the cohort, I'll go for a stage rollout. And I'll say, let's start with 10% of our devices in production. Memfault will sample the group of devices, select 10% of them, and start updating them. If everything goes well, we can increase that percentage up until we get to 100%. Here we go. And we're done. If we want to abort the rollout for one reason or another, it's simple. We click the abort button, and our update is pulled. The last thing I'll show you before we open up for questions is some of the statistics that we'll gather, so we can check which devices have updated in our cohort or not. We can look at what the current deployment, which deployment is currently in progress and who deployed it. And then we've got a few things like a way to enable and disable updates at the click of a button, or a schedule we can set so that devices might only be updated Sunday nights rather than in the middle of the day when they are in use. That's it for the demo. I will go back to my slides and we'll open up questions.
All right. Yeah, I'm Tyler. I'm going to be feeding François questions. Let me switch my camera. Cool. We have a couple good ones here. How about partitioning flash memory? Where are you storing these new firmwares that you're downloading? And then what happens to those basically if you firmware update successfully or not?
Okay, great. So what I'll do is, can you guys still see my screen, Tyler?
We can, yep.
Excellent. So I'll go back to my diagram. I think this is a really good question. So as you can see here, we now have a bunch of programs. Does this mean that we're using a lot of splash space? And then the second thing is, where do we store an update that's in progress? And so there's a couple of things there. The first one is where do we store updates that are in progress? If you have a lot of flash memory, the best thing to do is AB updates, right? So you have 2 slots for every program, and you'll update one of the slots while the other is in use, so that in the event something goes wrong, you can revert back to you haven't overwritten the running firmware. But unfortunately, most of the projects I've worked on haven't had the luxury of having that much flash. And so instead, one of the advantages of this architecture is that you can update things in place. And and still leave your device in a reasonable state. So for example, here, if you're trying to update your application, because your secondary bootloader is what's running the update code itself, you're actually running that program. And so you can update the application slots in line. You can overwrite it. You don't need additional space to download your updates. And so this makes it very compact. The second thing I'll mention is that all of these bootloaders, they're very small, right? Your primary bootloader probably fits in 16K of RAM of code space or even less, because all that it does is verify that the secondary bootloader is okay and load it, otherwise load the boot updater. And last but not least, some of these programs can actually share a slot. They can share a flash region, which is a little bit complicated, but if you look at this diagram, what you'll notice is that you'll never need to run your boot updater and your application at the same time. And in fact, the boot updater, which updates your secondary bootloader, is so rarely used that it's okay if it's a little cumbersome to use it. And so what you can do is reuse the application slots. And instead of having separate flash memory for the boot updater, when you want to run that program, you can load it into your application region of RAM of Flash and run it there. I know that's a slightly complex, and I might have needed an extra diagram to talk about that, but hopefully that gives you some things to think about.
Cool. How would you handle boot loops? Like, what is your favorite strategy to handle boot loops?
Yeah, I wanted to talk about this, but at some point I had to cut some of the content of this webinar. I had too many things I wanted to cover. So if you look, there's an interrupt post that I've written at interrupt.memfault.com, which is about how to write a bootloader from scratch. And it talks about how to handle boot loops. And so very briefly, I'll explain what I do. What you want is to have either a shared register. So for example, if you're using an STM32, the RTC register bank has what's called scratch registers that are persisted across boots. So you can use these to pass messages between the application and the bootloader. Otherwise, you can create a no-init region in shared memory that requires a little bit of linker script wrangling, but it's not too complicated. The important thing is that you need to be able to persist some data across boots, ideally in a location that isn't flash, so that's easy to write and read. And then keep track of how many times you've booted and whether or not the application stays stable for long enough. So in short, you keep a counter, and every time you boot, you increment that counter. And whenever your application runs is stable for, let's say, 10 minutes, you reset that counter to 0. And if that counter ever hits, a threshold, let's say 3, so you've booted 3 times, you stay in your bootloader and you stop loading your application, and you just wait for an update, so that you can override the application, which is clearly not stable. So I recommend you read my article on interrupts, but hopefully this gives you an idea on how you can track how many times you've booted and whether or not your application is stable.
Great. We have another question here. Does the architecture presented change substantially when you're considering secure updates?
Another good question. There's also an interrupt post about secure updates, and it was also something I wanted to cover here, but ran out of time. So we'll likely have a follow-up webinar about secure updates. But in short, the architecture does not need to change for secure updates, because what you'll do is you'll bake in your public keys inside of your secondary bootloader. So again, let me bring back my diagram. You'll bake in your public keys inside of your secondary bootloader so that you can verify the application before you boot it. And if you need to rotate your keys, which is quite common, you need to update your secondary boot. You'll do that by updating your secondary bootloader. So you'll use your boot updater, you'll update your secondary bootloader, and you'll have new keys hard-coded into your secondary bootloader. You might also create a more sophisticated system which lets you update only the keys, but this architecture would work fine to start.
How many more questions do we have time for, Colleen?
I have another 10 minutes.
Sweet. All right. Yeah, so I'm going to cover two questions in one here. Your firmware update, maybe it has multiple MCUs, maybe it's using multiple different libraries. What are your thoughts on like splitting up a firmware binary into little sub packages, and then what are best practices around that?
Yeah, so I go back and forth on this. In general, I believe that it is very difficult to keep a compatibility matrix across different microcontrollers. So imagine you have 4 MCUs and they each talk to each other on your board, and each of them is running its own firmware. Well, in my opinion, that becomes very quickly intractable from a versioning perspective, right? Like what happens, if you have, one MCU running version 1, another running version 2, another running version 3, and another running version 4. And now you want to update one of them. How do you check all the possible compatibilities and incompatibilities? The matrix, it's actually combinatorial. It becomes very complicated. So instead, what I recommend is however many MCUs you've got, I would update them all together. I would create update payloads that are a single update payload that contains the firmwares for all 4 of the MCUs. And I would download that payload. This is a case where you'll need some flash memory as staging. You'll want to download that payload and apply it to all the MCUs at the same time. So that instead of having to worry about cross-compatibility, you really just update the firmware in a unit. And you consider the system as the thing that's versions, not each individual MCU.
Awesome. Patch updates, any thoughts there? So it sounds like the particular concern here is not enough memory to do AB updates, not enough flash memory, maybe constrained on bandwidth too. I know that's a lot that comes up in commonly.
Yeah, so if you're really constrained, what I would recommend you do is you can actually still use the same architecture, but instead of updating full images, I don't recommend that you keep a patch RAM or a patch kind of regions of flash. I think that's a very old school way of doing things. It actually ends up wasting flash, in my opinion. And because we can update things in place, we don't really need it. This is kind of the patch RAM made sense when you had devices with read-only memory that you actually couldn't update, and you use the patch RAM as a workaround. Instead, if you are very limited in bandwidth, what you can do is push delta updates. So instead of pushing kind of a full update of your application, you can implement a process in your secondary bootloader which accepts a delta update. So it's an update image which tells you, instead of telling you here's the content of the full new image, it just tells you what changes to make to the existing image to arrive at the new image. So oftentimes they're just offsets and new data for individual sectors of flash. And you will, and then you can apply those updates to your application. And because with this architecture, we overwrite the application rather than do AB updates, it's very compatible with these kinds of schemes already. But as far as generating those delta patches, unfortunately, there's not a ton of great tooling for that yet. This is something that we're actually thinking about at Memfault, and we want to make easier. But you can get pretty far with just binary diffing to start.
Great. About 4 more here. Oh, 1 more. Anyways, does Memfault require any library to be integrated with your code or in your system firmware?
So Memfault provides many different functionalities. Today, I showed you the firmware updates parts, but we also provide monitoring, crashalytics, and metrics from your devices. And so the monitoring functionality requires the use of the Memfault SDK, which you can find on GitHub. It's available as source. The OTA functionality does not require a third-party library. We do provide libraries to make it a little bit easier if you want, but you actually can use it without them at all.
Great. Another good question here. What if the boot updater is in the process of updating the secondary bootloader and the power is shut off?
Yeah, so this is why we have our primary bootloader. So imagine we were in the process of updating the secondary bootloader and the power shut off. And so now our secondary bootloader is broken. It cannot work. And if we try to boot it, we're going to have a bad time. This is why we have our primary bootloader. Our primary bootloader will checksum the secondary bootloader, and it will see that it's not working properly. And so instead of loading that, it will go straight to the boot updater, where we'll try again to update our secondary bootloader. This is why we have that primary bootloader. This is exactly the case that we worry about. And thanks to that very simple primary bootloader that just does a checksum and loads the right image based on that, we can avoid those pitfalls.
Okay, another question. How is security handled for devices with very limited resources? And then, sorry, specifically around encryption. Do you recommend encrypting your firmwares, or is there another way to basically, securely update in that sense?
The thing with security and cryptography is that people always try to be clever and create their own solutions, thinking that they can find a good way around fundamental problems. And that realistically, rolling out your own crypto and rolling out your own security architectures is a bad idea and will almost always end in tears. So instead, what I recommend is using some pretty simple libraries. Like, for example, I'm a big fan of some of the elliptic curve cryptography that's become common for image signing and image encryption. And you can use, there's a couple libraries like the Tiny Crypto library from Intel, which includes a very lightweight, very low RAM implementation of an algorithm called ECDSA. And ECDSA lets you sign a firmware image with a single, using only like a single 64 bits number and verify that signature. I write about this on Interrupt. I recommend you go read it. It's the firmware signing blog post, and we will cover this in a future article. We have time for one more question, Tyler.
Cool. There is only one more, and I'm just going to follow up directly online. So that's it.
Awesome. Looks like we're right on time. So thanks everyone. Actually, I'll go back to this slide. Thanks everybody for joining us today. It was a treat chatting with you about firmware updates. There's much more on the topic we could talk about. So if you've got suggestions, email me at François@memfault.com or tweet at me on Twitter at BaldassariFR. We'll be sending the slides and the recording so that you'll have all this material. And I again recommend that you check out Interrupt and join our community in Slack. I wish you a great day and an amazing end of your week.